Alright, guys, let's do this. So, by the way, these slides, you have access to it. They're right here. Alright, so this part of this topic is about climate models. So, we use models when we have to explain phenomena that's quite complex. There's multiple things going on. And by now, you should have realized that um, studying climate, there's a lot going on. Right? So for any both weather and climate model, you need to take several things under consideration. And again, you may or may not be able to see this, it's kind of small, but again, you have access to the slides. I showed you where they were, so you can just access the slides. But independent of whether it's weather or climate, you need to take under consideration lots of things about the atmosphere, like clouds, even size of clouds, right? Anthropogenic emissions. By the way, anthropogenic means human based emissions. Atmospheric chemistry, which we haven't covered that yet. We will cover actually this week. Land, we used to talk about differences in land and albedo, ocean, and sea ice. So all those things you should take into consideration when we talk about both weather and climate models. And most of the models they use what they call Kepler. That is a there is a program that allows those different variables to interact together and how they balance each other out. The difference between weather and climate models is about time. Remember, I said climate, we're talking about a long period of time. Weather, we're talking about day to day, hour to hour, right? But climate, we're talking about long term. All right, so let's talk about two really important models. The first model is called Earth System Models, and sometimes it's abbreviated as ESM. And what it is a computer model that uses several equations, right? So there's an equation for all those variables. So use several equations to make predictions. And those equations connect variables such as temperature, mass of water vapor, and momentum. Momentum meaning that the Earth rotates, so the speed of the Earth's rotation. So this model uses grids, so it breaks the Earth into segments, and then it does those calculations for different segments of the Earth. The second model that's used is the IPCC model. So the IPCC is the Intergovernmental Panel on Climate Change. It is the United Nations body for assessing science. It's composed of, I believe, it's 195 countries. They don't do research. What they do is they have experts looking at papers of researchers around the world and they come up with reports. I actually have, do I have it here? I don't think I have it here. Anyway, they have reports that they release every couple of years or so about predictions that they can make. So this is the IPCC model, is the most powerful model that we have, and it's pretty much used to make projected outcomes in the future. Let's see. So anytime you hear about, especially in a scientific community, you hear about predictions for climate change, most of the time they're talking about the IPCC models or the IPCC agency. All right. A lot of times scientists create models of the past, and you might wonder, why do we need to know the models of the past? It's just so we can control and regulate the inputs in the model, right? Because we know what the conditions are right now, so we can use the past to check in to see how our models work. For example, here, if this is the predicted and this is the current one, then they can adjust the parameters to correct for that. So there's a lot of that that has to happen. Okay, with all that in mind, what are the predictions? So this is the IPCC model prediction, and they predict 4 different scenarios. So let me walk you through. First thing, as soon as you look at a graph, the first thing that you should look at is the title and then the axis. So the title says scenarios for 21st century. Here is gigatons of carbon per year. That's a load of carbon, gigatons of carbon. And this is by human emissions. And this is years. So you notice we are in 2021. This predicts all the way to 2100, so it's a long time. I believe all of them actually stop at 2080, so close to 60 years from now. All right, and then there are 4 different scenarios. In one scenario is we stop emitting carbon dioxide right away. The other scenario, we stop emitting carbon dioxide in a few years, like 2040. In another scenario, we stop emitting carbon dioxide 2080. And in the other year, we just let things roll. We do not change what we're doing. We just keep doing what we're doing. So let's look what this looks like. So if we don't do anything about it, the CO2 emissions in 2080, you'll be around here. Okay, so you can see what would happen. This is if we stop in 2080. Here is if we stop at 2040, and here if we stop right now. Okay, so that's how the model begins. So they create that model and then they make predictions, and they use 4 scenarios. And there's at the bottom over here, there's some explanation if you need to go back. Before we go through the rest of the predictions, I just have to, you know this concept, you may not know this term. Radioactive forcing is a direct measure of the amount of energy's budget is out of balance. So I don't know if you remember, with the energy balance, we have the amount of incoming and the amount outgoing. If that amount is different, that's what this radioactive forcing is about. It actually is a measurement of that. Okay, so it's the difference between the incoming and the outcoming. And it's pretty much never zero, right? If it is below 0, it means cooling. If it's above 0, it means warming. So this is the projected temperature. So what the IPCC predicted, they use, based on the emissions of CO2, they calculated the radioactive forcing, right, based on those 4 scenarios. Okay, then using that, they predicted the temperature. It's shaded over years, right? So temperature, this is temperature over years. This is the amount of out of balance of the Earth budget. You can think of that way. The Earth budget, when it's out of balance, this is how we measure it, and this is over the years. So the lines are shaded just to account for confidence intervals, meaning that there is some variability that needs to take into account. But looking at this, the minimum, right, so if we stop, the minimal increase in temperature would be about half a degree, and the maximum would be about 7 degrees, a little over 7 degrees. Okay, so those are the predictions. You might think, well, 7 degrees, that's not that bad. Remember, it's 7 degrees Celsius. In Fahrenheit, that's about 45 degrees. So another way for you to think about this is think of a really hot summer here. Let's pretend a really hot summer here. I haven't been in California actually for that long, but I've experienced summers here that are close to, what, 95 in a really, really hot summer. So that means that if there's this much huge increase in temperature, it can actually go up to 140. Right? That's really, really, really hot. So you just can think of that way. So remember when I said be careful with Celsius. Celsius can be misleading for us because we instinctively think of heat and temperature in Fahrenheit, and Celsius are much bigger than Fahrenheit. So you need to be aware of that. Anyway, so this is the predictions depending on the different scenarios. The other thing that they predict, I won't go through too much of this, they also predict precipitation. Okay, so this is the amount of precipitation that they predict, again, different case scenarios. Obviously, the worst scenarios predict more droughts and more floods, right? So that is what comes down to. Projected sea level rise, all different scenarios, even the one that's really low CO2, medium CO2 emission, high CO2 emission, they all predict sea level rise. There's two reasons for sea level rise. One is that warm water expands, not just warm water, a warm object expands, right? So the warmer something is, the more space they occupy. So because warmer oceans will occupy more space, the level of the sea will naturally rise. The other reason for it is that increase in temperature leads to increase in ice melting, right? So if glaciers melt, that water is going to be added to the water of the ocean, which is going to lead to, again, more increase in sea level rise. So that's what that's how the science of sea level rising comes from. And then the last thing is extreme weathers. So if you think of weather as being one of the products of differences in temperature, with those predictions, you will have increase in regional difference in temperatures, and increasing difference in temperatures will lead to increasing weather, extreme weather. That's what pretty much comes down to. So that's what the two models, they're most popular. The two models most popular, using what the IPCC generated with the 4 case scenarios. This is where we are at. Okay, that's it for this video. Next thing that you're going to do, since I have you here, is to look at data. Okay, and the data is right here, and you're going to create a graph. Now you have few options. You can use Excel or Google Sheets if you know how to use it. They're wonderful if you know how to use them. You can just use a graphing paper or just a piece of paper that you have, or you can try to do it here by drawing. It's totally up to you. And you're going to create a graph of this data. You need to think about a few things of how you're going to create this graph. It actually tells you where the x-axis should be, what should be plotted in here. So you're going to create those graphs, and then those 2 questions are going to ask you to predict. Okay, so your graph is going to be your model. Okay, your graph is going to be your model, and you're going to use your model to make predictions, very similar to what I explained here to you. By the way, I never mentioned where the data comes from. It comes from mostly satellites. Okay, so the data is collected through satellites around the world. Let's see what else I was going to say. And then the last thing you're going to do, this is virtual lab is really cool. You're going to be investigating at glaciers on Rainier. And that lab is waiting for you in your virtual textbook. All right, that's it for today.